Okay. Hello, everybody. This is Dr. Hussein again in Calculus and Linear Algebra. This is module number 4, where we will start talking about in this module. We'll talk about second order differential equation. We'll start with homogeneous and then we'll go for non-homogeneous second order differential equations. First of all, you need to remember that first order differential equation we differentiate once, but in second order we differentiate twice. So if we want to represent the, let me bring my color then. Okay, if you want to 7 minutes. Okay, if you want to represent the function, you will say it contain x, y dash and y double dash. Okay, example is this function y double dash minus 3y dash plus 10y minus 7x plus 4 equals 0 because this is homogeneous. Or this function, sometimes don't have y dash or y or constant. It doesn't matter, since we have y double dash, then this means that this is second order differential equation. Now solving this equation is to find the y, our subject, our y. Now, second order differential equation can be classified into linear and non-linear. In linear, as you can see here, this is the linear. The element of y dash, which is p, is function of x. Element of y is q, function of x. And if we have constant, we take it to the other side, it will be function of x. But in non-linear, p, q, r will be function of x and y, as you can see. Okay. Now, let's consider as example this equation here, y double dash minus 12x equals 0. I will take this part to the other side, will be positive. I will integrate first, so I will get y dash. So when I integrate 12x, x will be x squared over 2. Okay, 2 with 16, with 12, it will give 6x squared, and c is the constant. Now if I integrate again, I get y. Okay, so when I integrate it here, x to the power 2, it will be to the power 3 over 3. 3 with 6, it will be 2, x to the power 3. And c, it will be cx, and the constant, the new constant, d. Now if I sketch this equation, as you can see here, because of c and d constants are not, known for us, we will have infinite number of, let me say, curves. You give numbers for c and d, you have different curve. Now, if initial condition given as example y of 0 at x0 equal 3, and I substituted in the y, I can get d to be 3. So let me substitute for d here. The new equation is this. I have one more unknown, which is c. So the number of curves here reduced clearly. I need another initial condition to find c, so it will be specified more. So let's assume I have y dash of 0 equal minus 1. It means at x0, y dash equal minus 1. I substituted for y dash. Okay, I got c is minus 1. I back and substitute for c here, as you can see, minus 1. Then the equation now is clear. How many curves? One curve. One curve for the equation because I specify the constants. Now, as a conclusion here, in first order differential equation, we need only one initial condition to find the constant, because it's one constant, c. Okay, so y at specific x equals something, you substitute to find c. But because here we have two constants, c and d, then we need two initial conditions, one for y and one for y dash, to find these constants. Okay. Now for homogeneous, this is how it look like the homogeneous. As you can see here, A is the element of y double dash, which is d squared y over x dx squared, and B is the element of dy over dx, which is y dash, and C is the element of y, which is equal 0. This is homogeneous. Now, how we solve the homogeneous equation, second order differential equation? We solve it by solving what we call it the auxiliary equation, characteristic equation. Okay, how it look like this equation? It will look like this way. Have a look. A, which is the same constant here, m square equivalent to this y double dash, and B, as you can see here, B m, and C equals 0. This is second order differential equation. Sorry, second quadratic equation, we will solve it either by factorization, a quadratic formula, as example here, quadratic formula to find the roots m1 and m2. Now, based on m1 and m2, we will write the final answer as I will explain in the next few slides. So the idea is to solve this auxiliary equation. Now, from where this auxiliary equation came, I will explain later on, but just to know that we will substitute for y double dash by m square and y dash by m, and constant is we keep it. Now let's go for m. Now m, the constants, either they came as a real but different roots, okay? As example, I have m1 and m2, but they are not equal. Then the solution will be, directly we write the solution, y equal constant exponential, the first m times x, plus constant the second exponential the second m times x. Very simple and straightforward. You find them real but not equal, this is the solution. But if they are equal, we found them that m1 and m2 are equal. Then we write the solution between two brackets, a plus bx, as you can see here, exponential mx. What if they are complex? Because we have three cases for auxiliary equation. Either real, not equal, real, equal, or complex. Complex, we got as example here, m1 is alpha plus j beta, or alpha minus j beta for m2. Now how we solve it? We solve it in this way. Have a look. Y will be constant exponential the first root plus b exponential the second root. Now we need to simplify and convert. Take exponential alpha outside as a constant. What is left is this one here, exponential plus j minus j. We need to